Alrighty, so what we're going to be doing today is what's called optimization problems. So first, we're going to go through 5 steps that you should at least consider while doing these problems. And then we're going to go through multiple examples today. But really, just to get an idea of what we're doing with optimization is, you're going to have numerous examples, but it's something like optimizing volume or optimizing surface area. Using certain stipulations given, what would give you the maximum area, or what would give you the minimum amount of volume used in something. So that's the type of problem we're going to be dealing with, creating something that's a maximum, something that's a minimum. So step number 1, a general approach to solving these types of problems. Step 1 would be determine the quantity that has to be maximized or minimized. Determine, actually for this one, make it a little easier to read. Step 1 is to determine the quantity that has to be maximized or minimized. Again, like I said, we're going to be dealing with like maybe surface area, volume, something like that. Step 2, you're going to sketch a picture or write statements identifying variables or quantities. Most often, it's going to be really helpful to draw a picture with this one. So you don't have to be a great artist, but a picture is going to help very much on these problems. Step number 3, write a primary equation that represents the quantity that is to be optimized, and it may have more than one variable. Step number 4, if the primary equation contains more than one variable, so part 3 we said it may contain more than one, if it does, a second equation may have to be written to show the relationship between the two variables. Use the secondary equation to rewrite the primary equation. So like solving for one variable and plugging in for another. That way you don't have two variables within an equation. You can represent one in terms of another. And step 5 here, once you have done steps 1 through 4, you take the derivative and verify by a sign chart that the primary quantity is maximized or minimized. So that's going to be familiar to us. Those are the tables where you create the intervals and determine where it's plus or minus and determine if there's a max or a min. So these are 5 general approaching steps to solving optimization problems. I'm going to give everybody a chance to finish copying because I'm going to move this paper once we're done. How are we on this side of the room? Caught up? Okay. Allison, we're good. How are we over here? Justin, guys in the back, we caught up? Almost. Okay. Up front, a few more moments.
I'm good.
Sam? Okay. Colton, Ariana in the back, good? Caught up? Or?
Yeah.
Okay. Alright, so let's take a look at the first problem. So example 1. A manufacturer wants to design an open box having a square base and a surface area of 108 square inches. What dimensions will produce a box with maximum volume? What is the maximum volume? So they tell us up here surface area that we have needs to be 108. What dimensions will produce a box with maximum volume? And then we want to find that volume. So step 1 was determine the quantity that has to be maximized or minimized. So what are we maximizing or minimizing? Volume. That's what we want to find. So think about what they're giving us. And we can maybe use a picture to help us if we want to. So let's draw the picture to help us do number 1. So we're designing a box here. So we have a box. Okay, so we have some box. It says that the box is open on top, has a square base, and it tells you the surface area. So how do we find the volume of this box? Well, let's label. What do we want to label the base? It's a square, so all the bases are going to be the same. Let's call it X. And let's call this distance, because this one, the height of it, we'll call it Y though, X and Y. So the base, they're all going to be the same around, is going to be X, and this side, they'll all be Y. Across the top, that means they would be what? We don't have to label it, but what would the top be? They would be X's also, yep. Alright, so our primary equation. We're talking about volume of this box. How are we going to find the volume? Go ahead.
You multiply length times width times height, or x squared times y.
X squared times y. Length times width times height. Very good. X squared times y. Okay, so now it says we wrote the primary equation. You may have more than one variable. Step 4. If it has more than one variable, we need a secondary equation to be written to show the relationship. So what information do you think we can use to help form a second equation? Go ahead, Dan.
Well, we know that we have to have a certain surface area, so we can write an equation for that.
Yeah, we can use our secondary one. Secondary equation can be for surface area. So now we need to create a surface area equation for this box. Remember what they told you. They design an open box having a square base, and it has that surface area. So what would be the equation to find the surface area of our box? Not any box, but specifically the box that they talked about here with the variables we used. Go ahead, Dan.
X squared plus 4xy.
Okay, can you explain how you got those?
The bottom has to be square, so you have to do x times x, which would just be x squared.
Mm-hmm.
And since it's an open box, you don't do that for the top.
Very
You have
good.
4 sides.
Very
So
good.
you have to do 4 times the surface area of each side, which would be x times y.
Very good. Okay, now we know what the surface area is. That's 108. But we don't know anything over here yet. X squared plus 4xy. But what we can do is we can solve this in terms of y to plug in over here. So we need to solve this secondary equation for y. That's the point of this one. Solve it for y. So if you want to go through the steps on your own, you can, or you can look up here after solving it. You get y equals 108 minus x squared divided by 4x. So this is what we have to plug in for y now. Volume equals x squared times 108 minus x squared divided by 4x. Let's simplify this a little bit. So we're gonna multiply in the x squared. So volume equals 108 x squared minus x to the fourth over 4x. 108 x squared minus x to the fourth over 4x. We're good so far? Steps we've done? Okay. So now it says that we need to, well, it says we need to take the derivative, but I think there's something we can do to make this a little easier, because if we took the derivative here, we would have to use the quotient rule. What can we do first, Dan?
You can take out a common thing of x and get it over 4, and then you can put the 1 over 4 in the front.
So that's one way of reducing it. What I'm going to think of, though, if you think of this 4x here, you can have this split up as two different fractions. So the 108 x squared over 4x, you're going to have a 4 and an x that would reduce here. So you'd be left with 27x, because the 4 and 108 reduce, the x and the x squared reduce. Over here, you're going to be left with 1/4, because you have a 4 on the bottom, 1 on top. That's not going to change. And then you have x to the fourth over x, so you're going to get x cubed. So that's this reduced. So now we don't have to use the quotient rule. Are we okay with that simplification? All right, take the derivative. dv over dt, the change in volume with respect to time. 27x, if you take the derivative, you get 27. Bring down a 3, so you get 3/4 x squared. Okay, now think about what we're doing. This is an optimization problem. We're finding where something is a maximum, something's a minimum. We took a derivative. What should we do with a derivative once we take it?
Critical points.
Critical points. Set it equal to 0. Take a moment, go ahead and solve those for your critical points. Find what x should be. Anybody find critical points yet? Who has an answer? What should my x values be? Go ahead. Okay, when you solve, you get positive and negative 6. Why is Allison's answer half correct? Daniel?
You can't have a negative distance, so you really only have critical points.
So she's correct. She solved the problem correct. Mathematically, she's done nothing wrong. Just be careful that when you check your answer, think about what you're finding for. X is a side length here, so can x be negative 6? No, it has to be the positive. So the only one we're worried about, yes, you get negative and positive 6, but we're only worried about positive 6. Okay, we took the derivative, found the critical point. Let's make our chart like we normally would with a derivative to check. Again, side length, so we're starting at 0. You can't have a side length smaller than that. 0 to 6, and 6 to infinity, because we don't know how big it could be. And we're checking our derivative here, v prime. Is it positive or negative within those intervals? We're checking to make sure this is a maximum. So check whether it's positive or negative within the intervals. Any luck? Anybody find where it's positive, where it's negative? Thank you. Positive, then negative. So that tells us this is a what? A max or a min? It's a max. So that's what we're looking for, is something that would maximize the problem. So we know at this value it will maximize it. So we know the x value would be 6, but we need a y value. Well, we've already solved it for y, so now we can plug our x value in to find y. So find the final y value. Y is equal to what? Brianna, did you find a y value? 3, yes. All right. So I have x equals 6 and y equals 3. These are my two values where we found that it's at maximized volume. So what I can actually do now, I know the x, I know the y. You can plug them back into your volume equation you have from the beginning to find out what that maximum volume is. So volume equals 6 squared times 3. So the volume is equal to what? What is the volume equal to? Yeah, and its volume, 108 inches, it's cubed. So 108 inches cubed, that's the volume. So I'm going to erase a little bit of this because I need to put one more thing here and I'm running out of room. So I'm going to erase over here. So this is our final answer. We found the x, we found the y, and they wanted the volume. So we found that. But we're just going to make a statement. We know volume is maximized at x equals 6 because volume is maximized at x equals 6 because v prime, the derivative, changes from positive to negative. That's how we know the volume was maximized. Checking our signs. So volume is maximized when it changes from positive to negative. And that's your first optimization problem. Any questions on your first one before we try another? All right, let's go ahead to the next example. Example 2. All right, example 2. A box is built from a rectangular piece of cardboard that is 25 centimeters wide and 40 centimeters long by cutting out a square from each corner and then bending up the sides. Find the size of the corner square that will produce a container that will hold the most amount of soup. So first, think about the problem. What are we trying to maximize if we want to try to hold the most amount of soup in this box? Dan?
Volume.
Okay, primary is going to be volume again. So before we actually create the formula, let's draw the picture to help us create that. So we're starting out with a rectangular piece of cardboard. They're telling us that it is 25 here, and this would be 40. So 25 and 40. And it says from each corner, we're going to cut out a square so we can fold up the sides. But we don't know what this distance is that we cut in on these squares. So let's just call it some distance x. We don't know what that is yet. We cut in x from each side on the corners. X, x, x. You can label them all if you want to. I'm just labeling one of them. But this would be x here and this would be x here. Okay, so now let's try to create our volume formula. So think about volume. We're going to fold this up. The sides are going to be folded up. So what is going to be our base? What's going to be our height to find the volume of this box? Again, volume, length times width times height. Let's start with the height. I think this might be an easy one to see the height. So if I'm cutting in x and I'm going to fold that up, how high is my height going to be? It's going to be x because that's what I'm folding up. I don't know what x is yet, but I know that's my height. You have the rest of it, Dan?
Yes. So we know that the one side is 40 centimeters and the other side is 25.
Yes.
Because you're taking two squares off of each side, you're going to have to subtract 2x from each side.
Exactly.
So you'll get 40 minus 2x times 25 minus 2x times x.
Very good. So we know this is 25 here, but we're taking away this x and taking away this x. So 25 minus 2x. This is 40 minus an x, so 40 minus 2x. Multiply them all together, you have your volume. Do we have more than one variable? Do we need a secondary equation? No, we only have one variable in there, so we don't have to worry about that. What you should do next is start multiplying everything together. So I'm going to leave the x here for now. Multiply or FOIL those out. So the 25 minus 2x and 40 minus 2x. Should multiply those all out. I got 1,000 minus 50x minus 80x plus 4x squared so far. And then if I subtract my x's there and multiply that x in, I'm going to do two steps at once. I would get 1,000x minus 130x squared plus 4x cubed. Okay, so I have it simplified. I found my primary equation. I didn't need a secondary. I've simplified what I have. What should I do next? Derivative, v prime. (1,000 minus 260x plus 12x squared). And we need to try to simplify this as far as we can before we set it equal to 0 because it will make it easier. So, next step I have, we're going to set it equal to 0, but simplified version, you would have 4 times 3x squared minus 65x, so rearranging it a little bit, plus 250. So if you take a 4 out of everything, 3x squared minus 65x plus 250. Now try to factor that. So 0 equals 4. I think it will factor. There's some large numbers there, but it should factor. I have 3x minus 50, and what's my other factor? 3x minus 50, and then x minus what? X minus 5. Okay, so that's my factored form. 0 equals 4 times 3x minus 50 times x minus 5. I already have it equal to 0, so now I just need to solve for my factors. The 4 is going away. We don't have to worry about that. Each factor set equal to 0. What are my x values? I'm going to get 2 x values. Sorry, what was that?
50 over
Yep.
3, 5.
50 over 3, comma 5. All right, so let's think about this. We need to create our table now. And we need to make sure, like the last one, I had negative 6 and 6, but I could only use one of them. Can I use both of these values? So do I need to test both of them? If yes, why yes? If no, why no? Ariana?
Wouldn't it be yes because of a positive value?
Okay, I like her reasoning so far. She says they're both positive answers. We're dealing with side length, so a measurement must be positive. So far, I like her reasoning. Does anybody else have any reasonings, yes or no?
Well, I would say no because 50 over 3 is 16-ish, and then if you double that, so you're cutting into both sides, that's
Yep.
greater than 25.
Okay, so what you have to be careful of. Ariana is correct that they're both positive, so okay, it seems correct. They're both positive, which is a good thing to look at. So you do need to pay attention to that. But if you do 50 divided by 3, you get about 16, a little bit more than 16. So if you go to your picture, if you cut in 16 from this side and cut in 16 from this side, is there anything there to cut from both sides and fold up? Or are you going to overlap? Yeah, you're going to cut 16 this way, and then when you cut this way, you're going to cut into what you've already cut. So you cannot use the 50 over 3. But the 5 we are still able to use. So now we can create the table with 5. So I'm going to try to find some room here. I'll create it here. 0, comma 5. And then 5, comma what? Well, what is that distance that we could cut in? So that's what you need to think about. 16, more than 16 was too far to cut. How far can we cut, and how far could we still cut from the other side? What's the maximum distance we could cut in? Dan?
12.5
12,
centimeters.
yeah, 12 and a half. Half of 25. That's the furthest we can go, so we can cut the same amount from both sides. So 12.5. This is the table you have to find your sign. Find when the derivative is positive, find when the derivative is negative. And Dan, you already have that for us?
Yes.
Okay, what do you
The
have?
5 is a maximum because it would be positive on the left, negative on the right.
Okay, positive on the left, negative on the right. So we know that's going to be a max. So we know this value will maximize our volume. So what we can say, a 5 centimeter by 5 centimeter square produces a container of maximum volume because V prime goes from positive to negative. So I know that's squeezed in there a little bit. A 5 centimeter by 5 centimeter square produces a container of maximum volume because V prime goes from positive to negative. So they didn't specifically ask us what the volume was. We could, but they didn't ask us. They just said what value of X cutting into these corners would create a maximum volume container. So if we cut in 5 here and 5 here, and 5 here and 5 here on each corner and fold it up, that's the maximum volume you're going to get when cutting that. If you use any other value to cut in, you will not have a maximum volume within the container. Any questions so far? Are we okay with the procedure we're going through to find that? All right, let's go ahead and look at example 3 then. Example 3, we have a rectangular page that's containing 24 square inches of print. The margins at the top and bottom are 1.5. The margins on the left and right are 1 inch. What should the dimensions of the page be so the least amount of paper is used? So let's just start with the picture to help us out. So we know we're going to have some page. And we know within this page, we're going to have text written on the page. The margin on the top is 1.5. Margin on the bottom is 1.5. Margin on the left is 1. Margin on the right is 1. So primary equation. What are we trying to maximize? We want to know what? What are we trying to maximize or minimize? Primary equation. Area. Specifically the area we're writing on, but yes, area. That's what we're trying to minimize at this point. But let's get some more information from our picture. So that's the basic diagram right there. This total part of our picture here, in terms of y, what would this be? From here to here. Must be Stevie, huh? Dan? From here to here. In terms of y.
Let's see, and the margin down there, from the left and right is 1. Wouldn't that be y minus 2?
Y plus 2.
Y plus 2.
Yeah,
yes.
y plus 2. Because we don't know what this distance here is, that's our y plus 2. You can label that if you want to. I don't have a lot of room here. This spot here, if you want to look, this is y here. Okay? It's not going to be able to read that very good, but y is right here. We're going to call this one x from here to here. So this then is x plus 3. Yes?
Oh, I see, because that's the 24-inch area. Okay.
Yes, this is the 24-inch area here, where the print is. So this is x plus 3, this is y plus 2. Now, can we find the area? We want to try to minimize area, but we're trying to find amount paper used. So what should the area be? Dan?
Y plus 2 times x plus 3.
Yep. X plus 3 times y plus 2. Okay, that's our primary equation. Is it one variable or more than one variable?
More than one.
More than one. We need a secondary. Secondary equation. So what do we know about this print area? Specifically the printed area, what do we know about it? Okay, what is it? We know it's 24, so we can use that to help us. We know that's 24. What is it? How do you calculate 24 according just to the print area with the variables we had? X times y, that's just the printed area. So x times y equals 24. I want to solve for y to get rid of the y in my primary equation. So I can have 24 divided by x. But if I want to write that so I wouldn't have to eventually use a quotient rule and a derivative, how can I write 24 over x? Remember the power it's 2? It's the hint. Yeah, it'd be 24x to the negative first. Brings it up from the bottom. Okay? So now we're going to have area equals x plus 3 times 24 x to the negative first plus 2. And we have to FOIL that. Multiply it out. Area equals 24 plus 2x plus 72x to the negative first plus 6. 24 plus 2x plus 72x to the negative first plus 6. We can reduce that a little bit. We get 30 plus 2x plus 72x to the negative first. So we have our simplified version. 30 plus 2x plus 72x to the negative first. I'm going through this one just a little faster so we can try to finish it before the end of class. What's my next step? Derivative. So go ahead, take your derivative if you're already there. Your derivative would be 2 minus, simplified version, 2 minus 72 divided by x squared. 2 minus 72 divided by x squared. Again, set that equal to 0. And I will give you the answer for this one because of time. So after solving for x, you'd have to subtract the 2 over and multiply by the, yes?
What did you get minus?
Where? Right here?
Yeah.
Because you brought down -1. Power roll.
Oh. Yes.
Yep.
Yes, I see.
Or you can add this 72, sorry, to both sides, then multiply by x squared. And when you solve, you would get x equal to 6. So after solving, you get x equal to 6. So at this point, we have to check our table. Intervals 0 to 6 and 6 to... Do we have any idea how big this page is? No, we don't. So we're not going to say infinity because the page is not going to be that big. We're just going to put a question mark there. We know it's definitely going to be some value bigger than 6. We don't know what yet, so we're going to choose some value close to 6 to test it. We're not exactly sure where it stops, though, for sure. So now the derivative, check your signs for a prime. While checking them, within this interval you get a negative, within this interval you get a positive. So we know so far that's telling us it will give us a minimum. We know the x equals 6, so how can I find y? If I know x equals 6, how can I find y? Yeah, this secondary equation. Plug in 6 for x. Remember that x to the negative first is the same as 24 divided by x. So y is equal to 4. Okay, we're almost done. I know the bell's going to ring soon. So last thing we would have to do is plug into our area function, the x plus 3 and the y plus 2. So your dimensions would be, well, you have to add 3 to your x, so 9, and add 2 to your 4. Your dimensions are 9 by 6. Those are your dimensions of your paper. So your answer is 9 by 6. Those are your dimensions. Your explanation, you know it's a minimum because you went negative to positive. So that is the final answer for that one. 9 by 6 are the dimensions of your paper to minimize the amount of paper used. So I'll leave that up there for a moment. If you have more questions about that one, we can talk about it more tomorrow since we're cut short on time here. But that is the final answer.